Like we're just about there, folks. Welcome back, everyone. And it's official. Looks like we're about to finish off week 2, even though we just got started. That's always kind of weird, but hope you all had a great longer holiday or weekend and a nice holiday. I always like these when we have a holiday right after class started because it feels like you get kind of a break to get your schedule and routine in order as the weeks heat up, going on to weeks 3, 4, 5, and so on. But before we get started at all today, a couple quick announcements are that assignment 2.2 is due today. I don't have an official late policy in this class, which means if you get this in at any point in the semester, I consider it for full credit and I'll grade it and return it as usual. But the other thing to keep aware of in any class, in particular math class, is that the due dates are more for pacing's sake. And the best practice is really try to get it done as soon as possible. A lot of people got these assignment 2.2 done well ahead of the due date. That way it frees you up for looking at the course content that's coming up, the next assignments, your other classes, and so on. So even though there's no official late policy, if you think of these as hard due dates, that's a best practice. But if something goes sideways in your life, maybe a different class, maybe something else, then keep in mind you can turn in homework assignments, even if you had a weird week, an off week, for example. As far as the grading goes in the course, I do most of my grading on Fridays, and I'm going to attempt to get it all done on Friday. But sometimes that's a lot of grading. It can spill over into Sunday. But the major goal I try to make sure happens no matter what is I get your assignments back on the next Monday that we meet. So if you hand it in a hard copy, I'll have the marked up and graded hard copy to hand back to you. If you sent in your assignment 2.2 by email, you worked on it digitally, then I'll just email it back once I've graded the entire set. I wait till the due date passes. That way, if I have the whole set of papers and I'm grading them as one set, I can be as fair as possible and not forget how I graded one paper and then do another one a few days later and grade that differently. That's just weird, I'd say. So I try to grade them all as one overall set just for the sake of consistency. But those are my announcements to start us out. Any questions or comments at all, folks, to get us started today? Okay, maybe just a few more announcements, and then we'll go back to where we left off, example 5. Other announcements are, don't forget, we went over this at the first day of class, but we went over a lot of things. Basically, everything you might need in this class is somewhere here on this list of documents and links and such. Of things that people forget sometimes is that all the lectures are recorded. So if you miss a class, come here for the playlist. If you need to print out lecture notes, this is going to depend on your style for note taking. The blank lecture notes are always published right here. And if you're going back to study something that we did, you can either look at the video. The videos can be long. You have to play them kind of fast to get to where you'd like. Or we could just go back to this document. So this contains the work that we left off on all the way to example 4. So we're on example 5. If you notice that doesn't get uploaded and you're trying to look up this information to see how we did a problem, just let me know. The odds are I just simply forgot. There's lots of little files that have to be put in the right place after class. It's easy to miss a little thing. So we're going to pick up on section 2.3. We'll make a start in section 2.4 right after, but we'll be finishing that more likely on the next week. Then this one's week 3 here, which means at the end of week 3, I start updating information down here, saying the exact coverage on the exam, some review problems to take a look at, and that sort of thing. So I'm going to try to give it a little bit earlier so you'll have extra time to study and prepare. So I guess we're ready to get going. So let's get back to section 2.3. In section 2.3, and this is my opinion, I would consider these ideas, definition 2.20 on set extraction, to probably be the most important concept in all of section 2.3, because lots of mathematical sets get built out this way. And just for a quick reminder of how it works, we start by indicating all the elements in a universe. So some kind of large domain that we care about. Sometimes this universe is a small set of numbers. Other times it's an entire number system, like over here where it was the real numbers. So we're going to say we are concerned collecting all the elements in some set or some universe that satisfies a proposition or a condition P of X. That condition has to be true. And so when we checked it on this set here, we found there is no real number X, for which the condition x squared plus 1 equals 0 checks as true. Because of that, nothing belongs to the set, so we called it the empty set. Me personally, I'd like to write the empty set this way, just looks satisfying. But there's other ways. You could either write it that way, or this is always a nice way to indicate the empty set, the set with just white space inside of it, so literally nothing. Other condition we checked was the set of all positive integers. So z is the set of the integers. The greater than 0 that you see there in red, that was a typo that had to be corrected, is indicating strictly the non-negative integers, the positive ones. But when we factored this polynomial, we found two integers work for the equation, but only one belonged to the set, because the set first clarified the universe was positive integers, losing the -3 there. So that's pretty much how parts A and B went on these kind of problems. Part C, similar to a homework question, is longer but highly similar. We had to do a modular arithmetic to see under what conditions this equation balances, or rather, what integers makes that work. But any questions at all, folks, with this concept here before we go to the other concepts? Okay, at this point in the notes, this kind of follows like an algebra class or even a calculus class. In algebra, when you define functions, you'll go to a section that says defining new functions for mole. You're doing f plus g, f times g, f composed with g, all sorts of things like that. In a calculus class, you'll learn how to differentiate a function. And then you'll get to a next section that will tell you essentially how to take other functions and differentiate them, like the sum rule, the product rule, the quotient rule, and all those fun little rules from calculus. When it comes to sets, the building new sets from old sets is all of this stuff right here. And this becomes something we get really fluent with after we've practiced with it for a little while. There's two ways to think about all these set operations, complements, unions, and intersections. We can say, our author calls this formally, we define them as sets this way, or analytically. Other ways, if you're a very visual learner, you might like thinking in these kinds of terms, just seeing it as a Venn diagram. I'll support both approaches, and these are meant to be just kind of really small, fast examples to get us through these kind of problems. Or, excuse me, illustrate how the definitions work, rather. I'm not sure if I put enough white space, so we'll throw in some extra as we go. So for really fast examples, it says a complement of a set A with respect to a universe. In our problem, the universe is the integers 1 through 5. Is written this way. There's lots of ways to indicate a complement of a set. Here, our author indicates sometimes it's A bar. Sometimes people write down AC, kind of like that, unless your set is C, and then it just looks kind of weird to complement the set C. Our author's going to go with tilde, but if you've seen it in other notations and that's your favorite way to indicate a complement of a set, that's okay too. So it's going to be the set of all x's inside the universe for which x is not an A. And the thought here is when you say complement, you mean the piece that makes up the whole. So the set A, together with its complement, if we took them and put them together, we'll call that a union later, we'd be dealing with just the entire universe once again. So let's run through this definition. If A is 1, 5, and U is 1, 2, 3, 4, 5, we would say the complement of A, written this way, tilde in front of A, is, let's track the condition. It's all the x's in U. So we're concerned with this set right here. But the condition that has to be checked as true is that x is not an A. So looking through these, 1 will not be in the set because 1 is in A itself. Neither is 5. 5 belongs to the set A. So the only things left off here are 3, 4, 5. These are the elements inside the universe that were not in the set A. So we just write out the complement now as 3, 4, 5. Any questions, folks, seeing the complement in that way? Okay, so if this made a lot of sense, you're probably learn new information in a more analytical way. If this seems foggy, then probably you incorporate new information in a more visual way. So let's see if we can see it in these kinds of terms. So this is the complement of a set A. we inject this into our example, here's what it would look like. There's a trick to move this anywhere you want. There we go. But it sort of makes the formatting. Okay, so here's our set A. As 1, 5, that means 1, 5 would be here. Not sure if I totally like the way the author indicated the set A. The set A is the white space here inside. The universe includes also 3, 4, 5. I'm putting it outside the bubble for the set A, only because A didn't have those elements inside of it. So 3, 4, 5 is on the outside. And now when we take the complement of A, it's all the x's in the universe, 1 through 5, for which x is not an A. And that would be these right here. These are the entries, not an A. So that's a second way to see that kind of complement. Any questions so far? Yeah. Oh dear, looks like that was a mistake on my part. I should have said I need all the x's. So I have 1, 5 here, and this goes 1, 2, 3, 4, 5. Looks like I forgot some elements. I have 1, 2, 3, 4. The 5 is actually on the inside there. Let me try again on this one. Thanks for pointing out the error on this. Let's try again. So 1, 2, 3. Oh, I need to write 1 a little bit better. So I have 1, 2, 3, 4, and 5. Okay. This visual approach doesn't work too well if you don't put the entries in the right spot in the first place. So we want x's in the universe U that are not an A. So we have 1 and 5 are the two entries inside A. Oh, that's bad color coding. 2, 3, 4 are the x's that are not inside A. And those are the x's in the universe. So it should have been the 2, 3, and the 4. Let me double check. So we want all x's in the universe such that the x is not an A. So 2, double checking, is not in that set. Neither is a 3 in this set. 4 not in that set as well. I think we got it a little bit better on that second try. And 2, 3, 4 also highlighted in here gives us the elements we expect. So here's the set A. That's a little bit better color coding. And now this is the complement of A. Does that look a little bit better with that correction there? Awesome. Thanks for spotting that. Other questions so far, either in Zoom or otherwise? Okay, so that's our first set operation. And notice if we take the set A together with its complement, we just get back the whole universe once again. 1, 2, 3, 4, 5. We can say as a formula that's going to make sense once we discuss the union a little bit further. A together with, or union, the complement of A, gets you just the universe right back. Written, yeah, just as an uppercase U. So next operation we need to discuss is that one that we just wrote down with the pencil tool. That's referring to the union of two sets. So the union of two sets, we write out as this way. If you've done interval notation, you've probably used the union symbol quite a lot, just writing down your answers in interval notation. And it's just a collection of every element that's either in the set A or in the set B, or in both sets A and B if they happen to overlap. So written this way, that OR is actually really kind of special. That OR is considered to be an inclusive OR. And essentially, any OR that we write down in a mathematical way, we think of as an inclusive OR. So we mean, when we say inclusive OR, we mean X and A or X and B, or X in both A, B. So both events would be considered valid to get that whole OR going, which is kind of weird because if you say, for example, Mike goes to work or Mike stays at home, we always think of OR as exclusive. Either one happened or the other, but not both. But in this class, the inclusive OR is the default assumption unless we say otherwise. So again, it's just the collection of all entries in both of those sets taken together. So if we're going to find A union B on this one, we would write out A union B equals a set of all x's, again, such that x is either in the set A or in the set B. So one thing you might write is 1, 5, 3, 5, 7, but this has a small problem right inside of it. This set does not get us full credit because there's one little issue with it. Anyone spot the problem with writing out a union this way? It's not that it's mathematically incorrect. We literally took all the elements of A, all the elements of B, and threw them together, but it still has one subtle little problem going on with it. Exactly, the sets do not consider a duplicate entry to be a different element in the set. A set only lists out the unique elements. So even though this is correct to write down, the assumption with sets is that we're always going to write them as simply as possible. So this is really equal to 1, 5, 3, 7. So that's our union of two sets. Not as rough as this one, at least this one was a tough one for me to get going, but let's still indicate how this comes together if we saw it as a graph. So the union of two sets is indicated this way. If we're dealing with a Venn diagram, in this problem we had for A, it was 1 and 5. I want to put 5 right here in the Venn diagram because 5 is common to both the set A and the set B at the same time. So it would belong to the overlap. The set B also has 3 and 7. But 3 and 7 cannot go inside here. If we wrote a 3 above the 5, for example, we would imply 3 is inside the set A, but it only includes 1 and 5. So this ring for A is just those two entries specifically. And this circle for B is the entries 3, 5, 7. When we say A union B, we're just taking 1, 5, 3, 7, just all the entries that we see here in totality to build out that set. So this is the set A union B, seen two different ways. Any questions, folks, with the union operation? Okay. So unions are great. All we're doing is putting two sets together, but still watch out for this. Let's make this an official comment on the notes. We are still thinking in terms of sets, so we only list the unique entries. It's out of order, it looks weird, but that's okay because sets by nature are unordered. So only put it in order if it just makes more sense to you. It's completely optional. But let's say here, for this portion, we must write sets in simplified form where elements, or you could say entries, or components of the set, I'll go with the elements, are not duplicated. So that's 2 examples down. Again, they're meant to be kind of fast examples. And some people are probably very, very familiar with this kind of stuff. Think of it as just sort of a refresher in that case. If you're very familiar with it, this would be the bigger thing to focus on. How it's written down in this formal way, as our author says, in indicating the set. But for the next set operation is all about what's inside here. The entry 5, again, is pretty interesting once we're dealing with these kinds of sets in a Venn diagram, because it was common to this set and that set at the same time. So this whole region is interesting. We'll think of that as an intersection. And our intersection symbol is, well, intersection is sort of the opposite of union. So we just flip that symbol you see right there. If it's written this way, now we're dealing with the intersection of two sets. And instead of saying it's the collection of all entries that belong in one set or the other, the difference this time is intersection has the word and in the middle. So both conditions must be satisfied simultaneously now due to the and. Whereas up here, the union symbol just means one condition or the other, possibly both condition holds. So if we have the set again, 1, 5, 3, 5, 7, guess we're looking at it. Hang on, I deleted too much there. Guess we're looking at that set right up here. Oh, that's saying union. We can't take that one. Let's do this one for the intersection. So if we have again 1, 5, so here's the 1 and 5, 3, 5, 7, 5 is already listed there, so I'll just go 3, 7. Then the intersection of those two sets, we already kind of saw and talked about in the prior example. It's just the set 5. So we would say A intersect with B is a singleton set, meaning just one entry. That's a weird curly brace. The one entry is 5, because 5 is the only entry of A that is also in the set B. And really, that's all the work you have to do if you're just eyeballing the two sets listed out in this way. Go down the line. Entry 1 is not inside here since entry 1 is not in the set B. But entry 5 is, because entry 5 is common to both. Or you can think in terms of Venn diagrams and consider the common overlap. That gives you the intersection. So that's lots of examples so far. To me, the one that seems the weirdest is the set difference. We'll cover that one next, but any questions at the moment? Okay, so as far as set difference goes, this is one that's also written out in a lot of different kinds of ways. Instead of writing A minus B, other texts go A set minus B in this kind of way to mention the same kind of operation. So if you've seen that before, we're not doing anything different. Idea with doing a set minus is we're taking the set A and removing all the elements inside of A that happen to be inside the set B. So formally we say it's a collection of all x's in A, and at the same time, those x's cannot be in the set B at the same time. So take out all the B components of A, in other words. If we do it analytically as before, just eyeballing these sets, we would say A. I like to say set minus here to remind me it's not normal subtraction whatsoever. This is pretty bizarro kind of subtraction. So A set minus the set B means go to the set A. I have a 1 here. If there was a 1 in this set, we would not include it. But because there isn't, we just throw a 1 here and go off to the next entry, 5. 5 does belong to the set B, so it does not have this condition. This part is violated. 5 is in B. That means 5 does not belong to the set, and we just close the set brace in this way. So that's the whole set. A, taking out the components of the set B, or the entries of B. Visualizing a Venn diagram, I think it's a little bit more helpful on this one. Oh, this is the difference done 2 different ways. I'll do just the screenshot for A minus B. That's a little bit more relevant to us. So we had for the set A, it went 1 and 5 overlapping with B. The set B is 3 and 7. So, and what the Venn diagram is now indicating is all the set B gets deleted in the set, and we just write down the survivors, the entries of A or the elements of A, not in the set B. Well, that's our last operation, folks. Any questions with either one of these, running down the list? Okay, there's a lot more to discuss, but I would say this is a good list of things to come back to, take a look at. The homework problems are pretty much kind of like this, just really fast results. If you're really familiar with this, just think of it as a way just to polish your skills on these same kind of concepts, because they seem to come back all the time. Down below are the major diagrams that we were looking at before, and the definition of set equality. We said sets are equal if and only if both sets have exactly the same elements. So just for a really quick illustration of that, we say A is 1, 5, and B is 5, 1. And let's say C is 1, 5, 2. Then for a quick example, we can say A equals B. The entries are listed in a different way, but that's okay. The order that we enumerate the elements of the set does not dictate set equality. We would say A is not equal to the set C. Oops, let me get that away. Because the set C has different entries, element 2, which is not common to the set A. So that's what set equality is all about. More interestingly is these relations down below that we'll take a look at next. So think of these ideas of subset or proper subset analogous to being things like, say, 5 less than or equal to 7 versus 5 less 7. Both of these are true statements, and they're trying to convey what's said here. We'll say a set A is a subset of B if every element in the set A is also an element of B. There's got to be a good way to write that out. So let's write this down in a specific way. Well, actually, this does just fine. I think we'll leave it the way our author went. The definition down below is saying a proper subset, but that's just like we said when we were indicating 3 strictly less than 7. We would use this result if we know the entry we're dealing with, the element, definitely includes this relationship. If we had x here, and we didn't know what x was, we just know that 3 is less than it, we might say 3 is less than or equal to x if it has the possibility of actually becoming x. So that's what's going on with this relationship. We say A is a subset of B to include things along these lines. If A equals 1, 5, and B equals 1, 5, we would still say A is a subset of B in this way. The little bar on the underline is just a way to say it could also be equal to at the same time. If B is slightly bigger, 1, 5, 7, we'll still say A is a subset with a little bar under there of B in this way, but it'd be more accurate to just write it out this way. A is a proper subset because B is strictly a larger set. They're not actually equal in that sense. So we only write out a proper subset like this if we know for certain what the sets are and that they are actually not equal, for example. So we would always write, instead of 3 less than or equal to 7, we know what the number is. That's a true statement. It just feels weird. We'd rather write 3 is strictly less than 7, which is analogous to saying A is a proper subset of B. If we're not sure what the sets A and B are, this is the default symbol, proper subset or equal to B. That's probably a good comment here. So this is the default symbol. And this is the symbol we use if and only if we have more information, that more information being the sets A and B were not equal in the first place. So let's practice with these ideas down below here to see how they go. We have two sets, 0, 1, 2, 3, 1, 2, 3, 4, 5. We have a universe in case we need it, so 10 elements, 0 through 9. I'll leave this as a question for the class. Looking at the sets, is it true that A is a subset of B? In this way, with the subset equal statement. Some folks in class are indicating no, doesn't look like it's true. I agree with folks. Anyone see what one element of A would be to make this statement false? Absolutely. From the class, 0 is the problem. To be a true subset, we have to say every element of X in A is also an element of B. That's true for 1, 2, and 3. 1, 2, and 3 are in the set B. It's not true for 0. So we can say here, this is false. You could indicate this in lots of ways. You can say subset equal, like that, to say it's false. Just like saying 3 is not equal to 7. Just negate with a line through it, like you're just angrily slashing something out to make it false. So A is not a subset equal, sorry, try and get it erased there, of B. And in fact, it's also true that A is not a proper subset of B either. The larger question was about subset equal, since 0 is an element of A and 0 is not an element, we'll write out this way, of B. Yeah, and this is just a fancy way of saying, if we look at the set B, 0 is not inside. For something to be a true subset, if we're looking at it from the angle of Venn diagrams, it must be something along these lines. Here's the set B. I'll use the way our author indicates it. Here's the set A. I think we need a different color for that. Let's go with purple. Here's our set A. Going this way, in this relationship, A would be a subset of B. In fact, more precisely, the way we indicate this looks like there's elements inside B that are not in A. We would also say it's true that A is a subset of B as well. But our condition looked a little bit more, oh, can't do that. We have this statement as false, A is not a subset equal B, because our condition looked more like this. The set A kind of did that. One little piece extended beyond the set B and left it, and so we said it's false, not a subset at all. So subsets are, again, another part of mathematics that gets used everywhere. If you study statistics, the major goal of statistics is to take a universe, that's just your population, and then take a random sample. That would be the subset coming from the population that you're studying to analyze the entire population. And many, many other examples as well. Well, any questions, folks, with our first example here with sets and subsets? Okay, another really strange related question along the lines is A intersect B a proper subset of B? Again, proper subset means they're not equal to each other. And I think this one is kind of a tougher question because, nothing is definite here. We have to answer this question for any set A and any set B whatsoever. So let's give this a try. Is A intersect B a proper subset of B? Any volunteers for an inkling in one direction or another? I tend to agree with you. This feels like a yes. There is a small technicality buried in there somewhere, though, that we have to watch out for. So this is also a situation where, because the set A and the set B are not defined, they're arbitrary sets now, we have to worry about certain cases. We need to worry about the case if A is equal to B and the case where A is not equal to B in order to answer this question entirely. But I think if you had the inclination this ought to be true, you're on the right track. We just have to watch out for any fringe case. So here's how we're going to attack this question. The sets A, B are arbitrary. That means if we write down an example, that's just for our scratch work to try to get an idea of how it works, if things are going to work out for these kinds of things. But we have to answer the question for any set A and B. First, let's use this strategy. We have sets A and B here. Let's suppose this is scratch work at this point. We took A intersect B. Let's see. We need all the entries that are common to A and B at the same time. 0, we just discussed, is not in the set B, so it's not in the intersection. But 1, 2, and 3 are. So we'll start with 1, 2, 3. Because I'm looking at the smaller set, I'm done when I'm doing the intersection, but it doesn't hurt to take a look at the larger set. We haven't looked at 4 and 5. They are not in the intersection because they're not in the set A, so we are on the right track. So A intersect B is 1, 2, 3. That means it is a proper subset. I'm writing it this way without the or equal portion of the set B, 1, 2, 3, 4, 5. So yeah, it looks like that should work out, even with arbitrary sets. But again, A and B are fully arbitrary, so there are two cases to consider. There's a case 1, And a case 2, I'll write them as I double I. And here's how it goes. In case I, that's the more familiar situation we were looking at the example above using the old sets. Let's say the fundamental thing with this example was that the set A and the set B were unequal. So we'll say A is not the same set as B. So that's our case 1. The fringe case 2 we have to worry about now is that A is the set B. So now let's analyze both of these separately and give our overall answer to this statement. Any questions at the moment with the structure we've laid out? Okay, well, with the case here where A is not equal to B, let's use this as a guide. We can now say A intersect B, I'll write it out this way, then A intersect B. I guess I put parentheses right there above the red dot just to say, think of that as one overall set, but parentheses could have been dropped, not totally necessary. A intersect B consists of elements that belong to both A and B. So now when we wonder, is A intersect B a subset? It will be true because we can now say, then A intersect B is contained in the set B. Really, that's pretty much where this statement should end. Because if we look at the definition for subset, let's pull it down here just to get it in context. Let's read through this. We said A intersect B is contained in the set B. Let's say a better way. Is contained is kind of like flavor text, but our official way of saying it is a subset. Sorry for that technology trouble there, is a subset of B. Or in other words, you could just say here, I dot E is contained in B. So we said A intersects B consists of elements that belong to both A and B at the same time. That means everything inside A intersect B is inside B in the first place. So the B inside the subset, we just have to insist that elements in that set A intersect B is also an element of B. But that's by default, but from the nature of intersection, all the elements inside A intersect B are automatically inside B as well. So that takes care of that case. We could say that A intersect B is a subset of B. And now finally, since A is not equal to B, it is true that A intersect B, here's where I would probably want to use the parentheses just to emphasize this whole thing is a set, is a proper subset, so we don't have to write the or equals portion here, of B. So when it said proper subset, the whole question was, can you make that symbol go inside here and make a true statement? It is true in the case A is not equal to B, but in the case A is B, we do have a problem. Any questions first, folks, in case 1? Okay, so our answer to this conclusion in case 2 then is, if A is equal to B, here, A intersect B, whenever the sets are completely equal, is just equal to B. Well, it'd also be equal to A, but we were wondering, is A intersect B a proper subset of B? to be a proper subset, let's look at one other little condition here. The sets can't be the same in the first place. That last little line there is just saying it's either subset or equal to, but we excluded the case equal of equality when we said it's equal to right here. So here A intersect B is equal to B, and so A intersect B, if you write the proper subset symbol here, it's false, so we just put a slash through it. And now we've conveyed, in this case, it cannot be a proper subset, but that was the one fringe case to watch out for. So overall, we can make a statement. Overall, A intersect B, I'll use this symbol again just to shortly say, is a proper subset of B if and only if A wasn't B in the first place. Otherwise, this is always a true statement. Really, the whole gist of this problem right here is that it was about the word proper. If you took out proper entirely, just delete this, then you're going to write down statements that look like this, subset equals, and it's just always true, whether A is equal to B or not. So subset equals written that way is a nice forgiving symbol. But if you ever have to be very, very specific of the subset relationships, then you do need the proper subset idea. So this was a big problem just to make a big deal out of that and its purpose. Any last questions, folks, on looking at this problem? Okay, so aside from these weird kind of technical problems, we have one last weird technical problem, part C. Is the subset of A true? Again, A is an arbitrary set. It can be anything. It could be the set 1, 5. It could be an empty set in the first place. And we're still trying to ask the question, is it a subset? So let me use these definitions here as we attack this question. So is A a subset of A true? You know, this one is kind of unnecessarily tricky because if I use the proper subset statement here, we can never say this. The empty set is not a proper subset of itself because the empty set is equal to itself. You can say the empty set is a subset of itself in this way. So unfortunately, that statement is false, but this statement does work out. So I think the better way to look at this problem is, let's make a quick revision. Instead of subset A, let's go with subset equal. I think we can consider that a typo. I think this is the better way to look at this problem. We want the larger subset relationship, subset equals. So we are wondering, is the empty set a subset of A true? This has to be for any set. And some people say already, yes, it's true. And I do agree. Again, this is a fringe technicality case. We can't say it's a proper subset of itself because we exclude the cases where the set equals itself. So this is the better way to think about it, and it is true. Yes, the empty set, the set that contains nothing, is always a subset using the subset equal operator, this one right here, of any set A. But this actually has a healthy amount of debate revolving around it, even in the mathematical community, about the type of truth that we wrote out here. It's not the nicest kind of truth. This is called true. Let me write it out this way. Yes, this is true. And here's the word that we're trying to avoid when we can, but we can't always avoid it. It is true vacuously. And that's not a nice word. If someone says you have a vacuous personality, they're not trying to compliment you in any kind of way. Vacuous sounds like we're talking about a vacuum. Nothing's there. Yet we have something that's truth by nothing supporting it. That's not quite exactly what we're trying to say here. If you're really interested in vacuous truths, there's a lot of discussions just right here going around it. It is optional reading, but here's a way this truth is really vacuous. we take a look at the condition. To be a subset, we have to write out the condition. If X is in A, then it is also an element of B. So the statement is true since if X is an element of the empty set, then X is an element of A holds as true. This already looks weird. Let's highlight this part. Because the condition X an element of the empty set never occurs since there are no elements X in that empty set. So essentially what we're saying is the only way for the subset relation, A subset B, ever checks as false is you have to find an X in A that is not an element of B. That is impossible if you're dealing with the empty set because there are no entries in there whatsoever to make this check false. So we say it's true, but because there was nothing inside that set to give us a chance of checking as false, we say it's only true vacuously. But it is an important concept. We always think of this empty set as being a subset of any set whatsoever, as long as you're writing the subset equal operator right there, highlighted in red. Well, any questions, folks, at the moment with this concept? Okay, and just for the fringe technicality, let's put this here in a box. And let me just format this better by saying the empty set is not a proper subset of itself because of the technicality way that was defined. So in other words, empty set written this way, we would always put a slash to the subset symbol to say not a proper subset. However, the empty set is a subset with the quality of itself is true. So this statement in orange is just to say that statement works for any set A, including when that set A is replaced with the empty set in the first place, as bizarre as that feels. Well, we've got it, folks. That's dealing with subsets. I don't have too many more concepts here, but we're going to look into ideas about a partition, more ideas about a power set, and then that concludes this unit on overall concepts looking at set theory. So let's take a look at those next concepts. Any last questions or comments at the moment with this vacuous truth we took a look at? Okay, if it still feels really foggy, then I think that's kind of normal. That's how it felt like for me when I saw this concept for the first time. But the next chapter we're getting into is on logic, and we will get into vacuous truths in logic to give a lot more clarifying information. But for the moment, let's take a look at ideas with partitions and power sets. Those ideas start with the idea or the concept of disjoint sets. So we could say qualitatively, sets are disjoint if they have no members in common whatsoever. I like this concept though. Usually this is my check for disjointness. We say a set is disjoint if they are non-overlapping sets. In other words, A intersect B gives back the empty set. That implies A and B are disjoint. Sometimes people say, in place of disjoint, the statement mutually exclusive. That's considered a synonym. I think it's less favorable just because it takes a lot longer to say and write down. But mutually exclusive is also the same concept here. So let's take a look at a couple examples going down the lines of this. For the first one, we have the set Q of rational numbers, the set I of irrational numbers, and these would be disjoint sets. Really just by their definition, every entry inside the set Q has to be written this way. We can in fact write out the set this way, Q equals P over Q, such that P is an element of Z. We can say Q is an element of Z greater than 0. Now we've excluded 0 in the denominator. We've also excluded negatives in the denominator, but algebraically that's okay if the numerator can be negative. So that's the set Q, whereas I is a set of all X in R such that it's irrational, X itself, if it's in the set I, that just means X is not an element of Q. So that's a way to write down this set of irrational numbers. And as long as you put that there we go. X is not a rational number. So just by its definition, we've collected in the set I all the entries that are not in Q. This will imply immediately Q, the rational numbers, the fractions, intersect the irrational numbers, say square root of 2, pi, and so on, is the empty set, only because this part right here, there is no overlap between these two sets. And so we say Q, I are disjoint. So the real number system can be, in a sense, partitioned as the rationals versus the irrationals. For further examples, let's take a look at this one. If A is any set whatsoever, so these are always tougher problems because it's now an arbitrary set. We're wondering, is the set A intersect the complement of A disjoint? Let's leave this one to the class. How do folks feel about this? So far, folks in class are mostly saying yes. How about Zoom? Any contrary opinions? Does this seem like a yay or nay?
Looks good.
Awesome. I agree with folks on this one. Honestly, I think the better way to take a look at this one is look at a Venn diagram. We write down, say, set that goes like this. Here's my set A. Let me see if I can color code this. Here's my set A in blue. If we want to visualize next a complement, let's do that one in green. So here's A. This is going to be a complement. A complement is out here. It's all the elements in the universe U constrained inside this box. Sometimes people put the symbol U to just emphasize that's our universe, all elements in question. But A is all the elements outside of the set A. So visually, this is a picture of disjointness. A and the other set here, a complement, are non-overlapping sets. And so we'll say yes. A. Oh, hang on. Let me see how I wrote this. Is A intersect A comma. I think the way I intended to write this, sorry for that symbol there, should have just been a comma. I'm going to need to do a better job at proofreading these notes. Sorry for those folks who have printed this out. That should have been a comma, not an intersect symbol. That's a hard one to track. Let me put an extra note here. Again, I'm probably going to need to do a little bit more work proofreading these notes before I send them out live. Not an intersect symbol should have been there. So we can say yes, A, and the complement of A are disjoint. But really, this is more about the spirit of what a complement is. It's all the elements not inside the set A. So by really its definition, these are meant to be disjoint sets in the first place. And notice if you put them both together, A union its complement, that would just be the whole universe. So this is already, in a sense, a type of partition. Take all the elements of A, and then in the next set, take all the elements not in the set A, and we formed a partition with two sets. Well, any questions, folks, with that one there? Okay, one down below I would say is more of a routine homework style type of a question. We have three just random looking sets, 1, 4, 7, 10 for A, 3, 5, 7 for B, 2, 3. All we want to know is which sets are disjoint. Let's take a while and take a look at this. Anyone spot the disjointed sets?
A and C.
Yeah, absolutely. If we look at the set A versus the set C, we can now write down A intersect C is, always look at the smaller set. Neither 2 and 3 belong to the set A, so it's the empty set. And this tells us AC are disjoint. Looking at any other comparison, A to B, well, there's a commonality here. A and B have a common L tree of 7. So if we write down A intersect 7, or excuse me, A intersect B, we would get, let's see, just a set that contains the single entry 7. This tells us AB are not disjoint. This is in the orange pen just to convey, really all you have to say here is this statement here, and we've answered the total question. But it's good to know when things are not satisfying the property we're interested in, what goes wrong. So that's the problem with A and B. Only last comparison we need to take a look at is B to C, but they have a common entry as well. The entry or element 3. So we can say the same thing, since B intersects C, the element in common is 3. Another singleton set. We now know that A and C are not disjoint. So that's the concept with disjoint sets. Essentially, think of it in terms of intersection. That's a great way to think about it because you're practicing another set operation at the same time. The moment you get the empty set, you have a disjoint set. Well, it looks like we're just about done with the set operations. For example, 11, I think I include these here just because sometimes set membership is really tricky, especially when you compare it with subsetting. And then I have the last two examples, partition and power sets down below. So let's take a look at example 11. I feel like for a problem like this one, if it makes it to a final exam, I just would say indicate if each statement is true or false. I also would give the emphasis, no explanation is necessary if I gave questions like these. But we'll do the explanations ourselves just so we can see if these are true statements or false statements. So let's go down the list. First one we're asking about is, in part A, is the set X a subset of itself? Which we have to be careful with because we're also worried about part B. They look like they're very similar statements, but one is set membership, one is subset equals. Well, looking at part A, one thing hint we do have is that A is always a subset equality to A because of that little line there allows for, let's see it this way, because the subset equals allows A to be equal to itself. So by the definition of set membership, any set that looks like this with a subset equal operator would automatically be true. Whereas if you went like this, however, X subset X, this is false. Because here we're saying the proper subset operator, that excludes the case the two sets themselves are equal to each other. That's what we meant by proper, excluding that fringe case of A being allowed to be itself in the relationship. So how about this one, part B? Would folks feel like this one should be true or false? that one kind of just makes your head hurt, right? Because these operators, they make sense in the examples, but once you mix them together, they start to get really, really vague. I think that's the whole point to example 11, to really get these separated in our minds. Part B, another similar one is part C. These two go together really, really well. The difference is in part C, notice that the set containing X itself is in the larger set to the right. Whereas up here, that's not the case. So that means this one is false. And if we had to modify something right here to make it true, the modification would look like this. The problem is we said the set X is an element of the set X. Well, if we wrote it this way, X an element of the set X this way, that way it's now suddenly true. Because if we look to the right, X does occur as an element. So here, this reads as X is an element of the set that contains just X. Definitely true. But this is the cool thing about notations. Notation is important in this class. This is saying something entirely different. It's saying the set that contains the one element X is an element of the set that contains just X. Well, the set that contains just X does not also contain another element that's a set that contains X. That feels like we're talking in circles, but we're really not. That's just the slight weird notations that we have to deal with when it comes to subset and membership. So again, this one's true because that as an element is definitely there. It goes into that location. That makes this true. Whereas this one is false, and the only way to make this a true statement is remove the curly braces. So you're doing a check on just an element that's itself not a set in its own right. Well, last one. On part D, we're asking, is X a subset of the set that contains 1 and X? Let me see here. You know, that's a really tricky one. The more I look at it, the more I feel like well, there's two examples. I'm not totally sure on this one. Let's write down the second example. This could be written in a whole different way, right? We could say, what if we wrote, is X a subset equal of 1 comma X? So if we look at this statement, does the one on the right look like it's true or false?
I would say
So,
false.
so for false, let's take a look at the set definition again, or set subset definition again. Because again, these get really vague the moment you mix these operators. So let's go way up to here. Drop it down. Now let's take a look at this really, really carefully because we're at the moment where we can't make sense of what these operators are really saying. It gets very vague the moment our sets get a little bit more complicated. So we'll say, let's think of this over here as the set A and the set B as we run through this set definition here. A is a subset of the set B, written A subset equals, or you could just say subset. I'm just saying the equals here for the emphasis. If every X in A, let's go to the set A, there's one entry, we're calling it X. It has to also be an element of B. That means we're all set. This is actually true in this statement. So that's one way to look at this. Coming back over here, let's see if we can track the same definition with what we've got over here. So this is the set A. The whole thing over here is the set B. And very carefully, it says A is a subset of B, this larger set, if every X element in A, there's only one, it's just X, is also an element of B. And here's the conundrum. It's not an element of B when you really, really look at it, because the elements of B are an element 1 and an element that's the set X itself. This is actually false. The only way to make this a true statement is if we wrote it this way. The set X subset, oh, well, I guess we kind of did. It's right up here. If you take off the curly brace, you make it true. That's one way to look at it. But in this statement, we have a false statement since let's say it this way, false since the set on the right, again, this really hurts your eyes to looking at this the first time. That's why we're dissecting it very carefully. The set on the right contains elements 1, and the second element, because of the awkwardly imposed curly braces there for the sake of a trick question, is also element. None are equal. To X. So in other words, here's the related concept. X is not the same as saying the set that contains X. Again, really light, small fringe cases. But when we think of sets, we're really just talking about lists. These are things that really get implemented in computer programming languages. And these are the small kinds of things you have to worry about encoding in and of itself. So think of this as a very massive syntax problem that we have to be hyper aware of, or else set inclusion just falls on its face and makes no sense. And here's a slightly weirder way to look at this. You can make this true in one or two ways. The one way we thought about it was take off the curly bracket on that X right there, write out the set B in the way we're normally thinking of reading it. We have a true statement. Or you could do something even weirder. Come over here and say, I have a set that contains only X, and that is a proper subset, a subset equals of 1 and a set that contains just X, only because when we go to look at this definition, here's A, here's B, every element X in A, which is a set containing X, is also an element of B. B also happens to have a set containing X. So this statement would be true. The one above is true, but this right here is patently false. This is a good set of problems to come back and take another look at as you learn these kinds of ideas more and more, because again, I feel like part D is really, really subtle, but then it does make sense and becomes something that clicks the more you look at it and practice with it. Any questions or comments at all, folks, running through those? Okay, well, it looks like I took quite a bit of time on dealing with these set theory kind of examples. I'm glad we did example 11, even though it took a lot of time, because it's good to know the difference between these operators. But it also means we might not have the time to finish these notes on today's class. We'll be finishing this when we come back on Wednesday's class. So I'm also going to push back the homework assignment 2.3. There will always be a 1-week turnaround on assignments from the moment which we finish the very last problem, example 13. But it looks like we have time to do one more problem, idea of partitioning sets. And there's a lot of reasons why you might want to partition sets. One idea about this is we're trying to sometimes extend the idea of equality, like 3 equals X, 5 not equals 7, and so on, to larger and larger things. Later, when we extend equality, we're going to call them things like equivalence classes, in the sense that any element in here, even if, say, a 3 or an X, we would consider them to be equal if they belong to this partition. So at the moment, partitions just seem like, wow, we can take a set S and cut it up in this kind of way, but it has a huge mathematical purpose all at the same time. So all a partition is, well, it's a set of sets, not too different than this one. This is a set that contains a set inside the set, but everything inside the partition is a set in its own right. All those sets have to be non-empty. That's a strict requirement and kind of nice in a way. So every one of these sets in the partition we see on the right has some entries inside of it. Notice that right there, though. We insist that the subsets in the partition has to be at least one. That means the set S itself is considered a partition. Using itself, that's one set. Ordinarily, a partition is implying k is larger than 2. This is just a fringe case that's actually allowed for a partition. The requirement for the partition is that the union of all these sets, A1 through AK, is S. So if you think of this as A1, A2, fixing the 2, there we go, A3, A4, and let's say that's AK, K is 5 in this problem. Then saying that the union is all S can be visualized this way in this Venn diagram. There's no part of S that we have left out. This is also the next requirement. A partition implies that A1, A2 throughout, these are all disjoint sets, no overlapping. So we say AI and AJ are disjoint whenever I is not equal to J. That means we're not comparing AI to itself. That is not disjoint. We're comparing A1 to say A4, A1 to A2, and so on. So we want non-overlapping, i.e. disjoint sets for which the union is the original set S itself. If you can do all that, you've got an honest-to-goodness partition. So we're not going to do too much with partitions just yet. There's not too many in the homework problems. It's just a way to extend on dealing with sets like we've seen before. Let's write down our partitions for the set ABC. So this is actually a pretty interesting problem. To find the partition, we would write out this. Recall, it's a set of sets, so we start with the set itself. Now we have to say all the ways to break up ABC. First way is this, ABC. So this would be partition 1, much like say, partition 1 is taking k equals 1. It's using the whole set Y in this problem for its partition. But there are other ways to partition that set. You could say, for example, just take, for the next one, let me go like this. This is a weird way to write a partition because a partition is a set of sets. But I only threw one set inside there, so it's a set containing the original set Y. It just looks weird to read. But here's our next partition. We can start actually breaking these things up. If it's A, B, and C, just 3 entries, one thought is to go a singleton, and then the other 2 entries, B and C. So this is partition 2. And so on down the line. The next partition, we can just take the next element here, make it a singleton set. Let's go with B. Put in the rest of the entries, A and C. And then that's our partition 3. I'll stop listing them out, but I guess we can just say it this way. Here's our third partition. Keep on going. So next one could look like this. The singleton C. Next would be A and B. So let's take a look. This is partition 4. Guess I do want to say partition just out of clarity. And at this stage, well, let's take a look if we really have partitions in the first place. The union has to be the original set Y. So if I union A with B and C, we get A, B, and C. Similar here, union B together with A and C, we get A, B, and C. They also have to be disjoint. A is disjoint with B and C, B is disjoint with A and C, and so on. So we're definitely on the right track. Are there any further sets that folks can see to add to the partition?
Three singleton sets.
Absolutely, good call on that one. So the last partition is like the finest partition possible given the set. Let's go A, B, and C. And this actually gets us to a really interesting question I didn't know the answer to. One thing you might wonder about all this is, how do you know when you have the right number of partitions? We're actually done here. This is partition 5. That's all of the partial partitions. And you can now say the number of partitions. If you want to check this on your own work, on your homework, to see if you have all the possible partitions, the number of partitions is let's see, I wrote this down, Bell's number. This is a pretty interesting formula, so if you Google this, Bell's number for partitions, you get sent to a pretty interesting article for computing Bell's number. And they say the Bell numbers for the sets go like this. The sequence of Bell numbers are for the empty set 1, set with 1 entry is 1, set with 2 entries is 2, set with 3 entries is 5. That's the set we just did. And it is this formula over here where you're using binomial coefficients, all that kind of fun stuff. You don't have to compute the Bell number when you do this problem. But it's kind of interesting to know that there is a definite check on this if you're worried if you have all the partitions possible. Well, it looks like I ran over a minute on there. Sorry about that, folks, but any questions at the moment? Okay, when we come back next class, we'll look into power sets and then finally get into section 2.4. It's a lot easier to find the number of sets in a set. So we'll have a better formula for here to get on the right track in finding out the power set. But have a great weekend, folks. Sorry, only one class this week. We'll come back to finish off section 2.3, begin working on 2.4 on our next class. But have a great weekend, folks. If any questions come up, I'll be happy to help out.